My name is Ann-Kathrin Edrich. I'm a PhD student at the Research Group for Model-Based Development in Computational Engineering at RWTH Aachen University in Germany. Unfortunately, I cannot give this presentation myself during your meeting, but I'm really glad to have been invited to prepare this video to give an introduction into my research project and the topic of time-dependent shallow landslide hazard mapping. Nevertheless, their limited size, due to their swarm-like occurrence, shallow landslides still pose a threat to people, infrastructure and the environment. For hazard mitigation and land use planning, the generation of hazard maps is an essential tool, and machine learning has gained increasing importance in recent years due to the increased availability of especially also open access data and increased computational powers. In many studies that perform machine learning-based hazard mapping, the workflow to obtain these maps have to be implemented from scratch all over again. And therefore, in this project, we aim at providing a generic, scalable and modular workflow that can be adapted to individual research problems to generate hazard maps using machine learning. The workflow we implemented contains the same or similar steps as most machine learning hazard mapping studies. It starts with the conceptualization step. So, what's the research problem, which area of interest are we looking at, what's the resolution, scale, etc. After the data for the area of interest has been found, the workflow provides support in pre-processing these data sets. As they often come from quite heterogeneous data sources, in order to prepare the input datasets for the machine learning algorithm, these datasets need to be harmonized first regarding, for example, resolution, extent, coordinate reference system, and file format to allow easy and efficient handling. The next step is the actual hazard map generation through training the model and then applying it in the area of interest. And finally, the workflow suggests a validation strategy for the model through the validation dataset and or another independent third-party dataset. By setting up the workflow, we orient on the FAIR principles. And the technical implementation is done in Python, where we focus on a very modular implementation. It is a purely data-driven approach, which is currently based on a random forest classifier. The resulting hazard maps are binary, which means they provide information on hazard and no hazard. This workflow has been set up while working on the test case scenario of rainfall-triggered shallow landslide hazard in the Swiss canton Grisons. For generating the hazard maps for this test case scenario, we relied on open access data only to ensure reproducibility of our results. Before we can go to the time-dependent hazard mapping, I would like to take the opportunity to talk about the random forest and the necessary input datasets. The random forest is an ensemble tree algorithm that has been shown to provide good results in hazard mapping tasks. It is basically a forest of decision trees. Each decision tree makes an individual decision on the hazard potential of a certain location, and the final decision of the random forest is determined by majority vote among all decision trees. The random forest needs to be trained on data for all classes it's supposed to predict. So in my case, it needs data for both classes, hazard and no hazard. For the hazard class, we include in the training dataset so-called presence data. This is information on historic landslides taken from a landslide inventory. For the test case of this project, we use the WSL Hangmon database. For the no hazard case, we sample so-called absence locations. They are locations where we assume that no landslide took place in the past, and here we sample these locations randomly among locations fulfilling certain criteria. These criteria result in a sampling mast, which you can see here, where orange locations indicate possible sampling locations. The number of absence locations with respect to the available presence locations has a strong influence on the outcome of the hazard mapping. Choosing a 1-to-1 ratio has proven to be a preferable ratio in previous studies. The idea behind random forest-based hazard mapping is that the random forest searches for patterns in the environmental conditions of presence and absence sites and then investigates the environmental conditions of the area of interest for the occurrence of these patterns to draw a conclusion on its hazard potential. Chosen environmental parameters should be meaningful for the physical predisposition for the occurrence of landslides. but depending on the research area, due to limited availability, it might be necessary to use proxy data though. To ensure best results, a diverse representation of different environmental domains is desired. This is why we integrate datasets from the domains of topography in the form of altitude, slope and aspect, soil properties in the form of bulk density, coarse fragments, silt, sand and clay content and USDA classes, land cover and vegetation information, meteorology in the form of precipitation, and hydrology through the parameters of the soil moisture retention curve. The training dataset for the random forest has a tabular structure where each row represents either a presence or absence location, and each column is one feature, meaning information from one of the just presented datasets. One column also provides the labels that contains the information to which class the row belongs. This dataset is split into the actual training dataset that the model is trained on and the validation dataset that is used to check the quality of the model. The validation dataset, therefore, is a dataset that the model has not seen before and can be regarded as independent. Using the trained model, predictions are made on the entries of the validation dataset, and as the correct answers for the validation dataset are known, comparing the model's predictions with the correct answers yields an indication of how well the model works. For the prediction in the area of interest, which in my case is croissants, the whole area is basically considered as an accumulation of individual locations with the extent of the resolution of the final hazard map, which in my case is 25 times 25 meters. Each of these locations will be one pixel in the final hazard map. The same environmental features as in the training dataset are extracted from geospatial datasets for each of these locations and included as rows in the prediction dataset. The random forest makes an individual prediction for each of these rows and assigns each row a class, so a number either 1 or 0 for hazard or no hazard. The final list of ones and zeros is reshaped to the area of interest, which then forms the hazard map. For my test case scenario, this results in the hazard map here on the right. Areas in yellow indicate locations susceptible to slope failure. So far, what I've presented is time independent. All features are not subject to rapid changes, and therefore also the resulting hazard map is time independent. Time-dependent maps could capture the variability of the spatial distribution of the hazard according to the spatial distribution of the potential triggering event. An example would be a predicted heavy rainfall event that could trigger shallow landslides. The area in which the potential triggering event is predicted to occur should have a higher probability for the occurrence of shallow landslides than areas without any predicted precipitation. This spatial variability could be captured by time-dependent maps, and in the ideal case, hazard mitigation measures could be implemented more efficiently and more precisely. Well-suited parameter to achieve this would be precipitation due to its triggering nature, but also due to the increased availability of prediction and nowcasting products in recent years. So far, we've integrated precipitation as a time-independent parameter, which is the maximum precipitation at each location recorded in the period between 2000 and 2020. This is also a feature not subject to rapid change, and this is what we wanted to change in the next step. Therefore, we adapted the workflow to be able to account for time-dependent features to create time-dependent maps. The final aim, provided a good database would be available, is that equivalent to a weather forecast, a hazard forecast could be computed using, for example, next day's precipitation forecast to assess the potential for rainfall-triggered landslides in different regions of the area of interest for the time frame in which the precipitation forecast is valid. For this purpose, precipitation needs to be integrated in the training process in a way that it sustains its time-dependent nature. Precipitation in the prediction dataset is quite straightforward, as it would be as just mentioned, derived from, for example, tomorrow's precipitation forecast. Let's take a look at the training dataset, as this is a bit more complicated. The prerequisite to be able to generate time-dependent maps in the first place is the availability of the date of occurrence of the presence data, meaning a respective entry in the landslide database. From historic precipitation records, precipitation amounts associated with the landslide events can be directly extracted and introduced into the training dataset. This leads me directly to the major problem with time-dependent landslide hazard mapping using a random forest approach. What to do with the absence data? Due to the inherent definition that no landslide occurred there until today, there is no exact timestamp tied to them, and therefore we cannot get a single value from historic precipitation data. Therefore, we need to find a metric that is reasonable and meaningful for the lack of landslides at these absence locations. And we've spent quite some time testing different metrics, and I would like to quickly introduce 3 of them without going too much into detail though. The first metric we tried is the maximum precipitation, because the naive idea was if the slope didn't fail on the maximum it has seen, then why would it fail with less? And therefore we would enter this maximum precipitation value into the training dataset. For this purpose, I created a map you can see here that shows for each location in the map the maximum it has seen within the period of June 2000 to December 2020, which is the time frame for which NASA's GPM mission provided precipitation data at the time that I downloaded it. For the locations of the absence locations, the maximum is extracted and used as a metric in the training dataset. The second metric uses a random sampling of precipitation values, which should be especially valid if the study is large enough so that we can expect a reasonable distribution that reflects the actual precipitation patterns. The third metric we tested is based on the analysis of the precipitation patterns associated with the failure of the presence locations. The findings are transferred to the absence locations to derive a precipitation value for the training dataset. I want to quickly illustrate how we approached this. I will do so by looking at one exemplary landslide event location. For this location, we have a long-term precipitation time series from which we calculate a probability density distribution, as you can see on the slide. From historic precipitation records, we also know that the rain associated with the event for this exemplary landslide is 92 millimeters. By summing over all probabilities to the right of the red line, we get the probability that more rain occurs at this specific location according to the precipitation records than what is associated with the event. This probability can be determined for every single landslide in the database, ending up with many probabilities that can be used to define a probability threshold. This threshold describes the generalized probability that more rain occurs than is necessary to trigger a landslide, according to the analysis done on the landslide locations. For determining a precipitation value for the absence location, a respective probability density plot for every absence location can be calculated. From the absence location's probability density plots, the absolute precipitation value corresponding to the threshold probability can be determined, and these precipitation values can then be integrated into the training dataset. Well, that was quite a lot of information in a short period of time, but there are 2 important things I would like to highlight. Firstly, there are different metrics with individual advantages and disadvantages that could be integrated into the training dataset. And secondly, the integrated precipitation metric has a huge influence on the final hazard map. You can see here these 3 different hazard maps that only differ by the precipitation metric used for the absence locations in the training dataset. What generally can be observed is that the spatial distribution of the hazard for these maps often is quite similar, but the extent and overall total area of locations classified as endangered varies quite strongly. Therefore, it has to be concluded that time-dependent hazard mapping has a great opportunity to support precise hazard mitigation measures, but that further research needs to be conducted on suitable precipitation metrics for absence locations. Furthermore, it has to be said that many landslide inventories do not provide a timestamp for the recorded events and therefore cannot be used for time-dependent hazard mapping. With this remark, I would like to close the short introduction into my work on the event-based, generic, scalable and modular workflow for shallow landslide hazard mapping that we've implemented and our approach towards time-dependent landslide hazard mapping. Next to continuing to work on the presented precipitation issue, we are currently in the progress of investigating the transferability and scalability of the workflow I just presented, as well as the available landslide data. I want to thank you again for giving me the opportunity to present my topic. Please feel free to contact me in case you have questions or are interested in a scientific exchange, and the email address you can see on this slide. Thank you very much and have a great day.